Welcome back. My name is Matthew, and in this video we're going to be talking about double angles, the power reducing formula, and the half angle formula for trig functions. But the first thing that I want to show you is a formula sheet that I'm going to be referencing. This is something homemade that's not downloadable, and I haven't decided how to make it available for download. So what I'm going to do is I'm going to hide me, and I'm going to show you the upper half of this formula sheet and the lower half of the formula sheet. And if you want to go through the process of maybe taking a couple of screenshots and stitching them together and maybe turning it into one larger PDF, because the way that I have it, it does fit all on one piece of paper. So if you would like to have that, it's a really nice reference sheet. You can probably find this stuff existing somewhere else, but just in case you really like the one that I'm using, you can make use of it. My students have this available for download, but just in case somebody else is out there and says, "Ooh, I like the way that's organized," I'd like to try to set it up so that you can have it. I'm just not going through the motions right now of making it available for download. So let me see if I can pop this up on the screen for you. There you go. So here's the, let's see, maybe you want to, can I minimize that? Oh, that went away. Good. So let's see. I would say maybe capturing that half of the screen, and then let's see if I can get half angle formulas to just slide off the top of the screen. Is that going to show us the entire lower half of this formula sheet? It's so close. Not quite. All right, let me zoom out just a little bit. Let's do that one more time. All right, here's the bottom. You're not even seeing the entire bottom half of the sheet. There we go. All right, so half angle formulas go up just a little. Right, so from there down is sort of the bottom half of the sheet. Yeah, I'd say almost exactly the bottom half. And then from half angles up, if you want to screenshot that and drop them into an editor and stitch them together, have at it. I've been using this formula sheet for a long time. It's got a lot of really nice resources on it. And then let's come back into our notes. As we go through these notes, you're going to be seeing the formulas that exist on that formula sheet, which is nice. I'm going to be looking at my printed version over here, and let's see if we can solve some problems. First, we've got the double angle formulas, and there are a couple of alternate versions for the cosine double angle formula. And those are derived from a use of the Pythagorean identity. So in this original cosine double angle formula, we could take cosine squared and replace it with 1 minus sine squared, combine like terms, and you get 1 minus 2 sine squared. Similarly, if you were to replace the sine squared with 1 minus cosine squared and distribute the minus and combine like terms, you would get that cosine 2 theta is equal to 2 cosine squared minus 1, which is the first of the alternate formulas. So those are some of the tools that we're going to be using. Let's have a look at this first example problem. We're being asked to find the exact value of sine 2 theta under the given conditions. And I've got cotan of theta equals 3, or 3 over 1, and theta is in the third quadrant. And I'm such a fan, as you have figured out by now, of drawing diagrams, so I'm going to draw us in the third quadrant. Adjacent over opposite is going to be 3 over 1. That is cotan. There we are. Adjacent is 3, opposite is 1. But we're in the third quadrant, so my horizontal direction is negative, my vertical direction is down, which is also negative. So it's actually negative 3 over negative 1. And we can now use this diagram and the Pythagorean theorem to calculate the hypotenuse, which makes it the square root of 10. And we've got ourselves a pretty complete diagram. Now we need to evaluate the sine of 2 theta. Sine of 2 theta equals, what is the sine of 2 theta? I'm going to go to my trusty formulas up here. Sine of 2 theta is equal to 2 sine theta, cosine theta. 2, it's not much of a 2. Whoa. 2 sine theta, cosine theta, which is 2, and then the sine of theta is opposite over hypotenuse, which is, so we could put a little multiplication dot there, I suppose. Opposite is -1. Hypotenuse is the square root of 10. Cosine is adjacent over hypotenuse, -3 over the square root of 10. We do a little multiplication and we end up with 6 over 10, which reduces, of course, to 3 over 5. So our final answer as a fraction is 3 over 5, or 0.6. That's not too bad. They give us the left-hand side of a formula, we write down the right-hand side of the formula, and in this case we were able to draw a diagram in order to help us solve the trig functions that were on the right-hand side of that statement. Probably going to get a little bit more tricky. I'll tell you, in this section, actually, not all that much more complex. For example, here we have, so that I don't have to keep scrolling up and down, I'm just going to be referencing my printed version of the formula sheet. I look at my formula sheet, which is what I encourage my students to do because they get to use their formula sheet on their exam. And I'm looking at my tangent formulas. Let's see, we've been talking about double angle formulas. I see a 1 minus tan squared in the denominator. Hey, there it is. Tan 2 theta equals 2 tan theta divided by 1 minus tan squared theta. Yeah, it looks like my theta value is pi over 8. So on the right-hand side, you know, if these were thetas, and this was a theta here, this would match up with the right-hand side of what we saw on the formula on page 1. So the left-hand side of that formula says tan 2 theta. That's 2 times, but we know what our theta value is. They've given it to us. It's the pi over 8. So these are very much about matching up the pieces between what we're seeing in the given problems and what exists on the formula sheet. And matching those pieces to one another is going to happen a lot faster for you if you're familiar with the formula sheet. And the more you use the formula sheet, the more familiar you're going to be with the location of the various formulas. All right, so this is equal to the tangent of pi over 4, which is equal to 1 over 1, or root 2 over root 2, or root 2 over 2 over root 2 over 2, however you do it. The way we do it is root 2 over root 2, because we're halfway up into the first quadrant, which reduces to 1. Not bad. Looks complicated, right? 2 tan pi over 8 over 1 minus tan squared pi over 8. It's just a matching game. Match it up with that correct side of the formula. Power reducing formulas. This problem gets a little bit involved, and there's one particular opportunity for you to kind of stumble, and I'm going to point it out to you. There's also some arithmetic involved in this problem, which involves common denominators. I know we don't like common denominators, but we're going to do our best anyway. So I've got 10 times cosine 4x, which is interesting because none of the formulas at the top of the screen have a power of 4. So what the first thing I'm going to do is to write this as 10 times, and then in parentheses, cosine squared x, and then I'm going to square that whole thing. When we have a square being squared, we multiply the exponents, that makes the power of 4. Now, inside my parentheses, I have a cosine squared x. X, theta, whatever, it's an angle measure. I'm going to keep using x's even though the formulas say theta. So I have 10 times, and then in my parentheses, I'm going to replace my cosine squared x with the right-hand side of this statement, which is 1 plus cosine 2x. Remember, I'm using x's even though those formulas say theta, divided by 2. I'll close my parentheses and put that square back on the outside. Now, unfortunately, we have to start doing some arithmetic. I need to square what's in my parentheses. And remember that when you square a fraction, you get to square the numerator and square the denominator. So that's what we're going to do. I'm keeping the multiple of 10. In the numerator, when I square it, I end up with, I don't really need that parenthesis actually. Do I need that? I don't need that. When I square the numerator, and combine like terms, I get 1 plus 2 cosine 2x plus cosine squared 2x. And when I square the denominator, of course I get a 4. We could reduce the 4 and the 10 immediately. We could wait and do it later. I could slide the 4 over underneath the 10 and leave it as a 10 over 4 and deal with that later. You've got some options there. I don't know if one choice is better than another. Remember, though, that I got this from taking this and squaring it. And by squaring it, I mean I did 1 plus cosine 2x times 1 plus cosine 2x foiled and combined like terms in order to get the numerator that I've written in this fraction. All right, so the 10 over 4, I'm going to reduce it. Should I reduce it? Nah, let's just leave it as a 10 over 4. We can always reduce it later. I'll leave that as a 10 over 4, and we're multiplying it by the rest of this stuff. Oops. And I don't know, should we just leave it like that? Maybe we should distribute the 10 over 4? Let's do that. Let's distribute multiplication by 10 over 4. I'm going to take this 10 over 4 and I'm going to distribute it to the 1 and to this term and to this term. Let's see what that looks like. And if you want to write yourself a little note, we could write dist for distribute. So we'll write that as 10 fourths times 1 plus 10 fourths times 2 cosine 2x plus 10 fourths cosine squared 2x. A little bit messy? I don't know. As long as you're using a sharp pencil and you're using lined paper, unlike what I'm using, you should be able to keep that fairly tidy. Right, so let's simplify this, clean it up a little bit. I'm going to take the 10 over 4 times 1, which is equal to 10 over 4, and I'm going to write that that is equal to 5 halves. I don't know why I'm reducing now, but I'm going to. And then there's a plus sign. And then we're going to work with this term right here. So the 10 over 4 reduces to a 5 over 2. And the 5 over 2, the division by 2, is going to cancel out this 2 also. So we end up with just 5. Your other option is, think of this as 20 over 4. And 20 divided by 4 is equal to 5. So there's the 5. And the cosine 2x. And then a plus sign. And then it says 10 fourths cosine squared 2x. The 10 fourths is going to reduce to 5 halves. And, well, let's just leave the I guess we could change it now. So we've done some reducing in the first term, some reducing or simplifying in the second term. We took the 10 over 4 in the third term and reduced it to a 5 over 2. That's the last thing we did. And now I'm going to power reduce. I'm going to do it in the next step. Forget it. Cosine squared 2x. Okay, that way, if you want to write yourself a little note that the only thing we did in order to go from here down to here is we simplified or reduced. Simplify. All right, that's what we did. Let's try to not do too many things in one step, otherwise you read through this process later and it's even more confusing than it has to be. The next thing I'm going to do is power reduce this term. Power reduce. The 5 halves is still there. The second term of 5 times cosine 2x is still there. The last term still has the coefficient of 5 halves, but now we're going to power reduce the cosine squared 2x. Here is, we've done some arithmetic, which was not actually tricky, but you've got to have You have to be paying attention to make sure you get all that arithmetic correct. And then here's the real stumbling block that I mentioned initially. When we power reduce cosine squared 2x, and we use the power reducing formula, come up here to the top of the screen and look at this power reducing formula with me again. Notice that this angle measure says theta, and this angle measure says 2 theta. So what we did is we doubled the angle measure when we power reduced. We went from a trig function that's being squared to a trig function that's only to the first power. That's the power reducing process. When you power reduce, though, again, you have to take the angle measure and double it. Regardless of what the initial angle measure is, you have to double it. So I'm leaving that at the top of the screen, and then look straight down to here. You'll notice that this cosine squared is the cosine squared of 2x. When we power reduce it, we're going to have to double that angle measure, and it's going to become 4x. Not rocket science, not exciting, but could it mess you up while you're working a free response question? Or even on your way to a multiple choice option? Absolutely. And I should silence my phone. There we go. So let's power reduce that cosine squared of 2x. It's going to turn into, I'll put a multiplication dot there. So it's 5/2 times 1 plus cosine 4x over 2. So you see the 4x has appeared instead of just a 2x because we doubled the angle measure. If you want to highlight that, that's the thing you really got to watch out for in this particular problem. And then after that, it's all housekeeping. It's just a little bit of cleaning up arithmetic because we no longer have any powers greater than 1. Everything is to the first power. So let's slide this up just a little. I think I might just come... should we come straight down with it? Maybe yeah, I think I'm going to work my way straight down the page now. The first term is the same, still 5/2. Second term is the same, 5 cosine 2x. And then there's this third term. I'm going to multiply the numerators, so the 5 is going to distribute to those two terms, and in the denominator, the 2 is going to get multiplied by the 2. If you want to leave those rainbows on there, you can. I'm going to erase those and write this as a fraction still. 5 plus 5 cosine 4x all over 4. Because I know because my math skills are maybe a little bit above par, that's not exactly how I would have done it. I would have done a little shortcut. I would have done a little bit of work in my head. But I think that just multiplying those two fractions in sort of a traditional way by multiplying the numerators and multiplying the denominators is a good first step for you. And then what I'm going to do is what I call the distributive property of division. Just like the distributive property of multiplication, division plays by all the same rules, so we have to distribute our division. I'm going to take the 5 and divide it by the 4 in the first term, and I'm going to take the 5 cosine 4x and divide it by the 4. So we get 5/4 plus 5/4 cosine 4x. Again, not rocket science, but that's one of the little details that I recommend you watch out for. The last thing I'm going to do is, and that's a little note that you can write. You know, I've been slacking on my annotations that I usually write over here in the margin. Here you could write distribute your division. Here you could write DIST for distribute in the numerator. We didn't do any distributing in the denominator, we just multiplied those 2's together. And down here we're going to combine like terms. We've got 5/2 as a constant value and 5/4 as a constant. You need a common denominator. 5/2 is the same thing as 10/4. 10/4 plus 5/4 is 15/4. If you're thinking to yourself, You just did that too fast. I didn't do it too fast. You're supposed to know how to do that. I'm not trying to be rude, but you've made it to pre-calculus. You're supposed to know how to find common denominators and add a couple of fractions together. If you thought it was too fast, rewind it, play it back, listen to it very carefully. And if you already know how to add fractions together, I'm sorry I just went off about that. Ladies and gentlemen, this is your final answer as simplified as possible. Also, if you're still struggling a little bit with adding fractions together, I know that that's a thing we don't do very often. If you want some extra help with that, don't ever hesitate to ask even about those small sort of fundamental processes during office hours, at the end of class, sometime when you're not embarrassed that you need a little bit of assistance with that. More embarrassing is to not ask. Half-angle formulas. Yay, more formulas. Oh, and they've got these pluses or minuses in front of the square root symbol. Why are those there? What's the square root of 9? Plus or minus 3. Is that the plus or minus that we're looking at there? Bad news. It's not. It's a different plus or minus. I'll show you what that plus or minus does in an example problem. You can read the text that's written underneath those three formulas. I've never read it before. I don't want it to taint my explanation or interpretation of how to process the plus or minus, but you should read it so you have a different perspective. And there are a couple of alternate formulas for the tangent half-angle identity or half-angle formula. And we're probably about to lose the iPad for a moment, so if we go black for a second, we will be back. Here we're being asked to find the exact value of the sine of 105 degrees. We're going to solve this problem using a half-angle formula. We could use, excuse me, I make these videos too late in the day, obviously. I'm yawning in half of them. We could use a sine sum identity and rewrite this as the sine of 30 plus 45. We could write this as the sine of 135 minus 30. That would be in the middle of the second quadrant, minus 30 degrees from the first quadrant. That would take you to 105. But we're going to use the half-angle identity. So what I'm going to do is I'm going to rewrite this as the sine of 210 degrees divided by 2. That way, what this really says is the sine of theta over 2, which is a half-angle. And this half-angle formula up here says that the sine of theta over 2, if I can get to it, where'd it go? Sine of alpha over 2 or theta over 2 is equal to plus or minus 1 minus cosine over 2. Plus or minus the square root of, where are we? There we are. Equals plus or minus the square root of 1 minus cosine theta all divided by 2. Now, by matching, you can see that our theta value is 210 degrees, which means I'm going to make this theta value 210 degrees. And if you want to highlight those, not a bad idea, so that you can see how the pieces match up. Let's bring our equal sign down to here. And normally I address the plus or minus at the very end, but I'm going to switch it up this time, and I'd like to address the plus or minus right away. When you take the sine of 105 degrees, you're taking the sine of an angle measure that's in the second quadrant. And whether you use the mnemonic of all students take calculus or ambitious students take calculus, as I like to say, regardless of how you remember, when you take the sine of an angle measure that's in the second quadrant, you're going to get a positive answer. That's why there's a plus or minus in front of that square root symbol. It's like a reminder that you need to make sure that you put the correct sign in front of your answer. So I'm going to maybe I'll put a plus sign just to remind me as we go along that we were very intentional about choosing this to be a positive answer. Okay, now we're going to take the square root of 1 minus the cosine of 210 degrees, all divided by 2. Positive square root of 1 minus What's the cosine of 210 degrees? 210 degrees is 30 degrees more than 180 degrees. So it drops us 30 degrees down into the third quadrant. 30 degrees is pi over 6 radians. It's equivalent to 7 pi over 6. So we've dropped into the third quadrant just a little bit. You should draw that triangle. My students definitely know how to do that very quickly, very accurately, labeling side lengths correctly with negative in the horizontal direction, negative in the vertical direction because we're going left and we're going down. And then the cosine of 210 is adjacent over hypotenuse, which is negative rad 3 over 2. Negative square root, it's getting too small, negative root 3 over 2. So this does indeed say 1 minus negative root 3 over 2. And then I'm going to make this square root symbol a little bit taller because we still have to take all of that and divide it by 2. Is that really a square root symbol inside of a square root symbol? It is. Maybe you've never seen that before. This maybe was the first time I had ever seen it before when I was learning this stuff. So we still have a positive answer. If you don't want to keep bringing that plus sign along with you, you don't have to. It's okay. But underneath my square root symbol, I now have the number 1, which I'm going to write as 2 over 2, because that's equivalent to 1. The double negative turns into a plus. I still have the square root of 3 over 2, and I still have this big division by 2. What I did was I changed the number 1 to a 2 over 2 so that we have a common denominator so that I can do the addition of those numerators. So I'm going all the way to the left now, equals positive square root of 2 plus the square root of 3 over 2, all divided by 2. Well, when you take something and divide it by 2 twice, if you take a half of a half, you have a quarter. So this is equal to the square root of 2 plus the square root of 3 over 4. Or if you want to think of this 2 that's in the denominator here, if you want to think of that as being a 2 over 1, and then you want this to be a fraction divided by a fraction, and you want to keep change flip, then you'll end up with this 2 in the denominator with this 2, and 2 times 2 will make 4. This 4. However you want to get there, you need to get there, whatever's most comfortable for you. Remember that when you're taking the square root of a fraction, that's equivalent to taking the square root of the numerator and the square root of the denominator separately, so I can write my final answer as 2 plus the square root of 3. That still has to be underneath that big square root symbol, but then I'm going to divide all of that by 2. That's an unusual one. However, that's our final answer. I like to put a box around my final answer. And that was a weird problem. Square roots under square roots. So weird, in fact, that maybe we should do another one. The good news with problems like this is you can always check your work to see if you're getting correct answers. How am I supposed to know if the square root of 2 plus the square root of 3 all divided by 2 is the correct answer? Plug that into a nice calculator or type it into kind of a lousy calculator, but type it in carefully. Get yourself a decimal answer, and then use that same scientific calculator, hopefully, or graphing calculator, put it in degree mode and take the sine of 105 degrees. Should give you the same decimal. So you're capable of checking your answers on these. What is 157.5 times 2? Cosine of something divided by 2. 315. Where's 315 degrees? I work with radians mostly. I'm not even sure where that is. 315 degrees out of 360. Oh, it's 45 degrees short of a full rotation. So we're right in the middle of the fourth quadrant. Nice. So 315 is my theta value, and I'm just looking at my formula sheet, and I'm looking up the half angle identity for cosine. My sheet says that the cosine of alpha is equal to plus or minus the square root of 1 plus cosine of my angle measure, which is 315, all divided by 2. and off we go. I'm going to speed this one up just a little bit since I narrated the heck out of that last one. So this is equal to, I'm going to save the plus or minus process for the very end. Don't try to make the decision right now. See if you can make it at the end, and let's see if we get it right. So I've got plus or minus the square root of 1 plus cosine of 315 is the cosine of 7 pi over 4, or negative 1 pi over 4. Cosine's adjacent over hypotenuse, that's root 2 over 2. And we have to take all of that and divide it by 2. So that's equal to plus or minus the square root of 2 over 2 plus root 2 over 2. I've got to zoom in a little bit. My digital pen doesn't write that accurately when I'm writing that small. There we go. So that's 2 over 2 plus root 2 over 2, all divided by 2. Make sure that that's all underneath that square root symbol. Very nice. Equals plus or minus. Big square root still. Add the numerators together. That's a 2 plus root 2, all divided by 2, all divided by 2 again. You know now that the double division by 2 is equivalent to division by 4, so equals plus or minus a medium-sized square root this time. In the numerator, we've got 2 plus root 2, and we're dividing by 4 now. And you've been reminded that the square root of a fraction is the same thing as square rooting the numerator, which is the square root of 2 plus root 2, over the square root of the denominator, and the square root of 4 is equal to 2. Now, that's not our final answer because we need to make a decision about the plus or minus sign. And so I'd like you to look at the entirety of this problem, even if you need to pause the video right now, and try to recall how to make the decision about whether or not your final answer has a plus or minus in front of it. And it's not worth doing this problem unless you also know how to make the decision about the plus or minus. Because, especially in a multiple choice situation, you could have options A and B identical to each other, except one's positive and one's negative. So this is an important part of the process. I'm actually hiding a key ingredient in making that decision. It's the cosine of the original angle measure, which was 157 degrees. In which quadrant is 157 degrees? Well, it's a little bit short of 180, so it's in the second quadrant. And is cosine positive or negative in the second quadrant? The answer is, because it's adjacent over hypotenuse, it's negative. So our final answer needs to be negative. You can put the negative next to the fraction bar, or you could put it next to the square root. You could even put it next to the 2 in the denominator. I'm putting it next to my fraction bar. There you go. Nice job. Details, details, details. Keep paying attention to the details. What else do we have? Find the exact value of, hey, it's another half angle problem. This setup is a little bit different. They're not even telling us any of the angle measures. We want the sine of alpha over 2, given that tan alpha is equal to 8 over 15, and alpha is in the third quadrant. All right, let's see if we can churn through this one. Third quadrant, okay, I know how to draw that. And I'm going to move it down a little bit just in case I need to write something on top of that negative x-axis. There we go, that might be larger than I need it to be. Tangent is opposite over adjacent. That ought to be something like this, so that the opposite is shorter than the adjacent. However, it's to the left, which means it's negative. It's down, which means it's negative. This is a famous triangle. It's the 8, 15, 17 triangle. It's a Pythagorean triple. And now I need to evaluate the sine of alpha over 2. Now this is alpha, right? So alpha is an angle measure that's bigger than 180 degrees. It's bigger than pi radians. I'm going to put a little alpha there. We want the sine of alpha over 2. And our formula sheet tells us that the sine of alpha over 2 is equal to plus or minus the square root of 1 minus cosine alpha all divided by 2. Well, in order to answer the sine of alpha over 2, that means I need to figure out what the cosine of alpha is. So let's start working our way down the page here. This is equal to plus or minus the square root of 1 minus. Now from my diagram, I can see that the cosine of alpha which is adjacent over hypotenuse, is negative 15 over 17, and that's all divided by 2. So we've got some common denominators to figure out here, and they're different common denominators than we've been working with so far. There's my plus or minus. Here's my large square root symbol. I've got a 17 over 17. The double negative makes plus. There's a 15 over 17, and all of that is being divided by 2. I just made a mess out of that 17. That's better. And let's come down again, bring the plus or minus with us, keeping the large square root symbol. 17 plus 15 is 32 over 17, all divided by 2. And we're taking 32 seventeenths, and dividing it by 2. Well, if I had 32 apples and I divided by 2, I'd only have 16 apples left. Here I've got 32 seventeenths, and I'm going to cut that number in half, which leaves me with plus or minus the square root of only 16 seventeenths, or 16 apples. Now, the square root of a fraction is equal to the square root of the numerator over the square root of the denominator, so this is equal to 4 over the square root of 17. If you would like to, or if you're required to, rationalize your denominator, take that fraction and multiply it by the square root of 17 over the square root of 17, and you will get an almost final answer of either positive or negative 4 root 17 over 17. And now we need to make the decision about the plus or minus. This is like my favorite part of the process, I think. Maybe that's why I save it for last. Is it positive or negative? What am I even doing? Where does your eye go? Do you look at this part as you try to make the decision? Are you looking at this right here? If you are, and alpha is the angle measure that's in question, I mean, alpha is the angle measure that we drew in this illustration, right? Alpha is clearly larger than pi, because it pushed us all the way into the third quadrant. And I don't know, this thing right here says cosine alpha, so that's adjacent over hypotenuse. That's negative, right? Cosine's negative in the third quadrant. I'm intentionally trying to steer you in the wrong direction. See this equal sign and this one, and this one, and this one? I'm just working my way backwards through my equal signs, and this one, and this one, and this one, and this one. Where did we actually start this process? We started it here with the sine function. And what are we taking the sine of? Not alpha. We're taking the sine of alpha over 2. Alpha over 2 is our angle measure. Now alpha is in the third quadrant. So where's alpha over 2? I don't know. What might alpha even be? Well, if we took alpha and we pushed it as far as we possibly could into the third quadrant, it would be almost 270 degrees. Let's call it 270 degrees. Divide that by 2 and you get 135. Where's 135? It's in the middle of the second quadrant. So if alpha is as big as possible in the third, and you cut it in half, you end up in the second quadrant. Okay, so far we're in the second quadrant. What if alpha is just barely into the third quadrant, like 181 degrees? What's 181 degrees divided by 2? Well, 180 divided by 2 is 90, so 181 would be 90.5. So just barely into the second quadrant. I would say based on this diagram that alpha is larger than 180 degrees. Maybe it's approximately 200 degrees. You cut that in half, you got 100 degrees, you're for sure in the second quadrant. So alpha over 2 is in the second quadrant. You're taking the sine of an angle measure that's in the second quadrant. What is sine? Is it positive or negative in the second quadrant? In the second quadrant, opposite over hypotenuse is positive divided by a positive, which is a positive. So our final answer needs to be positive. I didn't write any of that down. You might want to rewatch the explanation of why it ends up being positive and take yourself some notes and put them right here, or put them down here with an arrow to the fact that, this is the question and this is the answer, the fact that this is positive. My answer is positive because alpha in the third quadrant, approximately 200 degrees divided by 2 is approximately 100 degrees, which is in the second quadrant. And I'm taking the sine of alpha over 2, which means I'm taking the sine of approximately 100 degrees, sine of 100 degrees. Since 100 degrees is in the second quadrant and sine is positive in the second quadrant, my final answer needs to be positive. Or some shorter version of that explanation. But that's the actual process that I went through in order to determine that my final answer for that problem needs to be positive. Verify the identity 2 different ways. Yeah, this is kind of cute. We could use the half angle identity. So this is sine squared alpha or theta over 2. We're going to use the half angle identity. So realize that sine squared of theta over 2 is the same thing as the sine of theta over 2 squared. And the half angle identity, so I'm going to pull the trigger on the half angle identity, or half angle formula as it's called on my formula sheet. We can say that this is equal to the sine of theta over 2 is equal to plus or minus the square root of 1 minus cosine theta all divided by 2. But we have to square that because we have that exponent of 2 on the outside. If you square a positive number, you get a positive. If you square a negative, you get a positive. So no matter what, we're going to be having a positive value on the left-hand side, or this is going to turn out to be a positive value. When you square a square root, those two things cancel out, and we're left with 1 minus cosine theta over 2. I don't see anything else that I can do. Do you see anything else we could do to 1 minus cosine theta over 2? It's not jumping out at me. But what am I trying to turn it into? I'm trying to make it say cosecant theta minus cotangent theta over 2 cosecant theta. That's crazy. How am I supposed to turn it into that? Well, what is, look at the top right corner of your screen here. What is cosecant? It's 1 over sine. What's cotangent? It's cosine over sine. And here's 1 over sine again. If I could make, look to the bottom left now, if I could make this 1 over sine, and if I could divide this by sine, and if I could introduce a 1 over sine here, I'd have it. I think that's what we'll do then. Let me show you how we're going to do that. I'm going to take this statement, 1 minus cosine theta over 2, and I'm going to multiply it by 1 over sine theta over 1 over sine theta. This thing that I'm multiplying it by is 1 over sine theta over 1 over sine theta. Anything divided by itself is equal to 1. So I'm really, in red here, I'm really multiplying by 1, which I'm allowed to do. It's not going to change the value of the expression, it's just going to change what it looks like. So now I'll take this and distribute it to the 1 and distribute it to the cosine theta, and I'll take this and multiply it into my denominator. And the result will be 1 over sine theta minus cosine theta over sine theta, all divided by 2 times 1 over sine theta. What a mess. What's 1 over sine theta? Oh yeah, it's cosecant theta minus cosine over sine, that's cotangent theta. And this is over 2 times 1 over sine theta. Oh, it's 1 over sine theta. That's cosecant theta. See at the top of your screen with those blue circles around it? Sure enough, we've done it. So we had to use the half-angle idea. Half-angle idea. I might be getting tired. The half-angle identity. And then we used a sort of a reciprocal identity. We multiplied by 1 over sine theta. In other words, we multiplied by cosecant theta into the numerator and denominator. And that got us where we needed to go. Speaking of getting where we need to go, we've only got a couple of problems left, so hang in there. In order to solve this problem using the power-reducing formula, I would say maybe it's even easier because we're going to get to borrow some of the work that we just did in this left-hand column. I'm going to remind you that the power-reducing formula for the sine function, so sine squared theta over 2, I might even write it down. Let's just write it down. The power-reducing formula says that that's an eraser. Tough to write with an eraser. Sine squared, I'm going to write it with alpha because this problem up here has thetas in it and I don't want you to think that we're actually working on the problem yet. Sine squared alpha is equal to 1 minus cosine 2 alpha all divided by 2. So remember that when you power reduce, you have to double the angle measure. So let's do that. I'm going to power reduce. So sine squared theta over 2 is equal to 1 minus the cosine of double the angle measure. That's 2 times the original angle measure of theta over 2, all divided by 2. I'm taking this angle measure, and doubling it with this 2 right here. That's this angle measure, and I'm doubling it with this 2 right here. See how those match up? Rewatch that again if you need to see all those match up. Okay, on the right-hand side of this equation, I now have 1 minus cosine. Oh, those 2's cancel. We've got cosine theta, all divided by 2. When I got to this point right here, and I saw that I had a 1 minus cosine theta over 2, I realized I've seen that before. So the rest of this problem in the right-hand column proceeds exactly the same way as the rest of the problem proceeded in the left-hand column, delivering us, yet again, 2 cosecant theta minus cotan theta all over 2 cosecant theta. Are you ever going to do this in real life? Absolutely not. Are you practicing problem solving and very complex thinking right now? Absolutely. Is that going to benefit you later? Probably. And finally, the relationship between the cone's vertex angle theta and the Mach speed, capital M, of an aircraft that's flying faster than the speed of sound is given by this relationship. Sine of theta over 2 equals 1 over m. And if it happens that theta is equal to pi over 6, we would like to be the ones to determine the Mach speed, m. Well, that looks like it's going to be pretty easy. All I've got to do is take the theta value and plug it in, right? So we've got the sine of theta, which is pi over 6 over 2, is going to equal 1 over m. So all we have to do is figure out what the sine of pi over 6 over 2 is. Well, that's the sine of pi over 12. Wait, I don't know how to find the sine of pi over 12. We're going to have to use our half-angle identity. My half-angle formula says that the sine of alpha over 2 is equal to plus or minus the square root of 1 minus the cosine of my angle measure, which in this case is pi over 6, all divided by 2. I feel like we've done this before. So let's march through this fairly quickly. That's equal to plus or minus the square root of 1 minus the cosine of pi over 6 is root 3 over 2. We're going to take all of that and divide it by 2. That's equal to plus or minus the big square root of 2 over 2 minus root 3 over 2, finding the common denominator there, still all being divided by 2, which is equal to plus or minus, still have the big square root, subtracting the numerators, that's a 2 minus root 3, divided by their common denominator of 2, divided by the big 2. We're dividing something by 2 twice, which is the same thing as cutting it into 4 pieces. So I will write this as plus or minus a medium-sized square root of 2 minus the square root of 3 divided by 4. And we said that the square root of a fraction is equal to the square root of the numerator, the square root of 2 minus root 3, all divided by the square root of the denominator. The square root of 4 is equal to 2. So that should be our final answer, right? It used to be, it's not anymore. Let's do that one last step of determining whether our answer should be positive or negative. What are we actually taking the sine of? At the top of the screen right here, we're taking the sine of effectively pi over 12. Pi over 12 is in the first quadrant. The sine function is positive in the first quadrant. All of our functions are positive in the first quadrant. So we do have a positive value here, which is the square root of 2 minus root 3 all over 2. Now, remember, this is equal to 1 over m. And we're trying to solve for m, not 1 over m. So we're going to take the reciprocal of both sides of that last stage of the equation. I'm going to take the don't circle it. Take the reciprocal and what do we get when we take the reciprocal? We find that 2 over the square root of 2 minus root 3 is equal to, you could call it m over 1. I'm just going to call it m. I'm also not going to double rationalize my denominator. If you want to do that, you go right ahead. This is for sure the right answer. You could plug this into a calculator and get a decimal equivalent. And then if you want to go through the process of double rationalizing your denominator, you can. Just make sure that you got the correct answer by finding the decimal equivalent to what you got after the double rationalization, compare it to the decimal equivalent of what we have here, and make sure that they're the same. And that's it. My eyes were getting tired anyway. As always, thanks so much for joining me. Next video for the next lesson, right down there. Check it out. Like or subscribe if you like what I'm doing and if you want to get notifications when the next videos release. And I'll see you around. Thanks again.